In this session, we discuss about sample link analysis. In previous sections, we have developed the basic link parameters relationship. In this session, we use that relationship to calculate sample link budget. The below table may appear the house of formidable listening of terms. One can get the false impression that the link budget representation is a complex complication. Just the opposite is true. We introduce a assertion in the below figure. We have reduced a set of line terms to key parameters. The goal of a link analysis is to determine whether or not the required error performance is met by examining the EB by N naught actually received by comparing it with the EB by N naught required to meet the system specifications. The principal items needed to determine are the EIRP, the G by T naught figure of merit, and LO, that is loss and degradation. By considering all of these, the link budget details shown in below figure consisting of 3 columns of numbers. Only the middle column represents the link budget. The other column consisting anchored information such as antenna beam width are computational to support the main tabulations. Losses are bracketed in the visual bookkeeping way. If you have a value is not bracketed, it represents a gain. The subtotal are shown in enclosed in a box. Starting from the top of the middle column, we are algebraically sum of all the gains and losses. The final link margin results shown in double box. The computational are performed in the equations which are repeated here with the expectation that the terms G and temperature T naught and together G by T naught instead of being listed separately. We know that M margin under dB is equal to EIRP plus G by T minus EB by N naught minus R minus K minus LS minus L naught. All is under dB. Once go through the table, we examine a few parameters based on this list. In the first one, the transmitting power is 100 watts. Circuit loss between the transmitter and antenna is 2 dB. Transmitting antenna gain is 51.6 dBi. The net tally items EIRP is 69.6 dBW. The path loss has been calculated for the range shown in the table title, corresponding at a 10-degree elevation angle at the terminal. And 6 and 7 here are allowance made by the weather fates and variety of unspecified losses. And 8th one, received isotropic power referred to the power would be received is minus 143.1 dBW if the receiving antenna were isotropic. The peak gain of the receiving antenna is approximately equal to 35.1 dBi. And edge of coverage losses is due to the off-axis antenna and increased range of users at extreme edge communication coverage. And the next one, the input power to the receiver tailed from 8, 9, 10 is minus 110 TWh. System temperature is found in the above equation. However, in this example, we are assuming the losses line from the receiver antenna to front end. So, that the line loss factor L is equal to 1. System temperature is computed by Ts is equal to Ta plus Tr. We form the receiving figure of merit ratio G by T naught by combining the gain of the receiving antenna G with system temperature T. The ratio placed in the left column are the parameters of interest rather than the middle column. This is because of gain is accounted for a link budget items 9 and TS is accounted for a item 15 if G by T naught where the place in the center column is would be represent a double tabulation. And Boltzmann constant is minus 228.6 dBW by kHz. Boltzmann constant is under decibel plus the system temperature is under decibel yields noise power spectral density. Finally, we can form a received signal to the noise spectral density is 82.5 dBHS by subtracting the noise spectral density is under decibels from the receiver signal in decibels. The data rate is listed is under data dB by dB bits per second. Since EB by N naught is equal to 1 by R PR by N naught, we need to subtract R in decibels from the P by N naught is in also decibels and consider EB by N naught is equal to 19.5 dB. And implementation loss here we taken to be 1.5 dB accounts for the difference between theoretically predicted detection performance and performance to the actual detector. This is our required EB by N naught, a result the modulation coding chosen and the probability of error specified. The difference between the received and required EB by N naught is decibels yields the final margin. So these are the parameters we consider in the tabulated from the 1 to 21 at a frequency of 8 GHz with a range of 21,915 nautical miles from the transmitter to receiver. The gain or loss in the items shown in link budget generally follow the conventional of first presentation and ideal and simplistic result, followed by a gain or loss term that modify the simplistic yielding of actual result. In other words, the link budget type typically follows the modular approach to partitioning the gains and losses in the way of easily adapt to needs of any system. Consider the following example of format in the above table. Item number 1 gives transmitting power that would be launched from the transmitter with isotropic transmitter antenna. However, only after applying the modulus of the circuit loss and transmitting antenna gain we can see. And EARP is also launched. Similarly, coming to the item number 8 shown power received by the isotropic antenna. However, only after applying the modulus of the receiving transmitting gain and edge of the cover loss, we seen that received signal power. And this is a simple example of link budget analysis. At the time of calculation of link budget analysis, we have to declare that these 21 parameters as a marginal values under dBs. So once we fix the distance between the transmitter to receiver, we must follow this link budget analysis parameters as a reference based upon the fixed frequency and based upon the range between the transmitter and receiver. If maybe in some cases the noise effects may be change the link budget analysis values, but it is considerable noises and considerable losses, we have to change those parameters depend upon noise produced by the environment. And now our next topic is receiver figure of merit. An explanation of why receiving antenna and system temperature are often grounded together as G by T naught is as follows. In the earlier days of satellite communication development, the G and the T were specified separately. A contractor who agreed to meet these specifications would need to allow himself some safety margins for meeting of each specification. Even though the user was generally only interested in the bottom line performance and not in applicate values of G and T, the contractor would not be able to export the potential of trade-off. The net result was our specified system was necessary. Recognition of such a over specification results in the specifying of antenna and receiver front end as an single figure of merit parameter G by T naught. Such the cost effective trade-off between the antenna design and receiver antenna design might be employed. Coming to the received isotropic power, it is another recognized area of over specification in the receiver design is in the separate specifications of required PR by N naught and EB by N naught. In the receiver side, G by T naught. If P by N naught and G by T are specified separately, the system contractor is forced to meet each value. The contractor will plan the margin in both places. As the G by T naught case for the preceding section, there is advantages of specifying P by N naught and G by T naught as one parameter. This is a new parameter called received isotropic power RIP, and it can be written as RIP is equal to P by N naught minus G by T plus K. In the other terms of ratios, it can be also written as RIP is equal to P by KT naught into KT naught divided by G, that is equal to P by Z. It is important to note that P by N refers to the prediction signal to noise ratio spectral ratio required for the particular error probability when using a particular modulation scheme. Let us designate the theoretical required SNR to yield a particular PB as PR by N, and it is also written as P by N is equal to L into PR by N. The L is implementation loss and the accounts for the hardware and operation losses in the detection process. By combining all these expressions, finally we can give the value of received isotropic power RIP is equal to LP by KT naught into KT naught divided by G. Specify the RIP required to meet the system error performance allows the contractor to commit the meeting a single parameter value. The contractor is allowed to trade off P by N naught versus G by T and loss performance. As G by T naught is improved, the detection performance can be degraded as vice versa. So that's why a contractor must be focused on P by N naught value versus G by T naught value by considering of loss performances. So that's why received isotropic power plays a crucial role at the received power margin declared by the receiving device. And one more important topic here we discuss satellite repeaters. Satellite repeaters retransmit the message they receive with a translation in carrier frequency. A regenerative, maybe digital, repeater regenerates, that is demodulate and reconstitute the digital information embedded in the received waveform before retransmission. However, regeneration repeater only amplifies and retransmit. A non-regenerative repeaters therefore can be used with many different modulation forms simultaneously or sequentially without any switching. But a regenerative repeater is usually designed to operate with only one or very few modulation forms. A link analysis for the regenerative satellite repeaters treats uplink and downlink as a two separate point-to-point analysis. To calculate overall bit error performance of a regenerative repeater link, it is necessary to determine separately the bit error probability of a uplink and downlink. Let us consider PU and PD, the probability of bit being is error on the uplink and downlink. Respectively, a bit will be correct in the end-to-end link if either a bit is corrected on the both uplink and downlink, or if it is error on both uplink and downlink. Therefore, the overall probability of the bit correct error can be written as PC is equal to 1 minus PU into 1 minus PD plus PU plus PD. Now, the overall probability of the bit error can be written as PB is equal to 1 minus PC, that is equal to PU plus PD minus 2 PU PD. For all the values of PU and PD, the overall bit performance is approximated simply by summing of individual uplink and downlink bit error probabilities. PB is equal to PU plus PD, where PU is probability of uplink, PD is probability of downlink. Based on all this, we declared bit correct probability, that is PC, bit overall probability PB. But the summation of PU plus PD must be equal to 1. Now coming to the second part, non-regenerative repeaters. First we discuss about the repeaters and then we go for the non-regenerative repeaters. Link analysis for non-regenerative repeaters treated the entire round trip, means uplink transmission of the satellite and downlink retransmission of the earth terminal as a single analysis. Features that a unique non-regenerative repeaters are the depends on the overall SNR on the uplink SNR and the sharing of the repeater downlink power in proportional to the uplink power from the each of various uplink signals and noise. Henceforth, the reference to a repeater or transponder will mean the non-regenerative repeater. For a simplicity, we will assume that the transponder are operating in its linear range. A satellite transponder is a limited of transmission capacity by its downlink power. The earth terminal uplink power, satellite and earth terminal noise and channel bandwidth. One of these usually is dominant performance constraints. Most of the downlink power or the channel bandwidth proves to be a major system limitation. Here the figure explains the important link parameter of linear satellite repeater channel. The repeater transmits all uplink signals without any processing beyond amplification and frequency translation. Let us assume that there is all multiple simultaneous uplinks with the receiver bandwidth W and they are separated from the one other through the use of technique called frequency division multiple access. FDMA communication resource sharing technique where the different users occupy different disjoint portions of the transponder bandwidth. FDMA is treated in the next chapters. The satellite effective downlink power EIRP is constant, and since we are assume the linear transponder, EIRP is sharing among the multiple uplinks is proportional to their respective input power levels. The transmission starts from the ground station, say terminal with I, with the terminal EIRP is equal to P into G. Simultaneously, other signals are being transmitted to the satellite. The EIRP from the kth terminal will henceforth be referred as a simple as PK. At the satellite, the total power is equal to sigma AK into PK is received, where AK is the reflected the uplink propagation loss and the satellite receiving antenna gain for each terminal. NSW is the satellite uplink noise power, where NS is composite noise power spectral density due to the noise radiated into the satellite antenna and generated in the antenna satellite receiver. The total satellite downlink EIRP is equal to PS into G, where PS is a satellite transponder with the output power and G is satellite transmitting antenna gain. And finally, we can express these equations based upon identity EIRP is equal to EIRP beta AIPI plus PT minus AIPI plus NS into W. Based on all these equations, we can finally conclude that the power received by satellite is equal to shown in 5.58 equation. To facilitate our discussion, let us simplify the equation in the above. Then the received power is shown in PRJ after the 5.58 equation, where S is the signal power and N is the noise power and U by L is uplink power. In the above equation, we can recognize that important relation that must exist among the multiple users. The users must cooperate with one another but not exceeding agreed uplink downlink transmission power limits. The above equation states that the portion of downlink EIRP dedicated to any one user is determined by the ratio of the user uplink to the total uplink signals plus noise power. Hence, if one of the sharing users should choose to cheat by increasing his power and uplink power, the effect would be enhanced for the users of downlink signal. At the expense of other user downlink signals. Notice that in the above equation, the uplink noise shares the downlink resource along the other users. The coupling up of uplink noise onto the downlink is a feature of unique to non-generative repeaters. It is shown in figure equation 5.59 and 5.60. The calculation of a P by R and calculation of a EIRP explain the uplink repeater noise degrade the overall SNR into two ways. It steals the downlink EIRP and contributes the total system loss. When the satellite uplink noise dominates, that is when PT is less than NSW, the link should be a uplink limited. And most of the downlink EIRP is wasteful allowed to uplink noise power. When this case, when EIRP is greater than NW, we write the above equation in 5.61 and 5.62 manner. The above equations explain that the case of uplink limited channel and the overall P by N ratio essentially followed by uplink SNR. The power of transponder is the shared primarily among the various uplink transmission signals. A very little uplink transmission is transmitted on the downlink. The performance of the repeater is constrained only by its downlink parameters. Here, the link analysis examples for the non-regenerative repeaters explained in the below table. The uplink portion by itself doesn't constitute a link budget since the transmission is not demodulated at the satellite. Without demodulation, there is no bits and there is no way to measure the bit performance. After full round trip, the signal is demodulated at the earth terminal. Only does the link analysis will be merged. In the above example, represent the case where the satellite and transponder is servicing 10 simultaneously users. In this example, we all users transmitting a same power level. Each of the signal is allocated 9.8% of a downlink EIRP. In the block, we represent a link budget is the example of non-regenerative satellites with a frequency of 375 MHz and downlink of 275 MHz with a range of 22,000 nautical miles. Most of commercial satellite transponder designed as non-regenerative. However, it seems clear the future commercial systems will be required onboard process, switching and selecting message addressings and will have regenerated repeaters to transform the received message into message bits. Besides the potential for sophisticated data processing on the principle of advantages of regenerative compared to the non-regenerative repeaters is that uplink is decoupled from the downlink, so that uplink noise is not retransmitted to the downlink. There are significant performance improves possible with the regenerative satellites repeaters in terms of EV by N0, values needed to be uplink and downlink. Relatively, the value is needed for the conventional non-regenerative designs is used today. Improve as much as 5 dB uplink of 6.8 dB as a downlink using QPSK modulation scheme. And it is also considered as a reference for the table. Coming to the non-linear repeaters. Power severely limited is the most satellite communication systems and inefficiencies associated with the linear power amplification stages are expensive to bear. For this reason, many satellite repeaters are employ non-linear power amplifiers. Efficient power amplification is obtained at the cost of signal distortion due to the non-linear operation. The major undesirable effects of the repeater non-linearities are: first one, due to the intermodulation noise due to the interaction of different carriers. The harm is to be twofold. Useful power can last from the channel as IM energy, and superiors of IM product can be introduced into channel as an interference. The latter problem can be quite serious. Second one, AM to AM conversion is the phenomena common to non-linear devices such as traveling wave tubes. At the device input, any signals envelope fluctuations undergo a nonlinear transformations and the result is amplitude distortion at the device output. Hence, a TWT operation is a nonlinear region would not be optimum amplifier choice for the amplitude based modulation scheme. Third one, AM to PM conversion is another phenomena common to nonlinear devices. Fluctuations in the signal enveloped produced by the phase variations that can be affect the error performance for the phase based modulation scheme. And the fourth one, the hard limiter. Peak signals can be suppressed relative to the strong signals as much 16 dB. In saturated TWT, the suppress of the weak signal due to not only the limiting but also to fact the signals coupling mechanism of the tube optimized in favor of strong signals. The effect can causes weak signal to be suppressed by much of 18 dB. Based on all this, conventional non-generative repeaters are generally operated back off from their highly nonlinear saturated region. This is done to avoid appreciable IM noise and thus allow efficient utilization of the system entire bandwidth. However, the back off to the linear region is compressed. Some level of IM noises must be acceptable and achievable useful level output. And coming to the last topic here, system trade-off. The link budget shown in the table in the above as a resource allocation document. With such a link tabulation, once we can examine the potential system trade-off and attempt to optimize the system performance. The link budget is a natural starting point for consideration of all sorts of potential trade-offs. Margin values, noise figures, antenna size versus transmitting power, and so on. Here the table represents an example of computer exercising for examining a possible trade-off and the earth station transmitting power. The system noise margin of the receiving antenna terminal. The first row is the table of above indicating the link budget. Suppose a system engineer is concentrating 500 watt transmitter is not practical because some physical constraints with the transmitting earth terminal or such a transmitter makes the system uplink reach. The engineer must be consider the trade-off transmitting versus thermal noise margin. The listing of candidate trade-off is a trivial task of a computer. It is shown in the figure table 5.4. The table 5.4 generates repeating a link budget computational multiple times at each time of iteration, reducing transmitting power by half. The results in the section transmitter and uplink and downlink and the overall SNR and the margin associated with each transmitter value. The system engineer need only pursue the list of to find likely candidates. For example, if an engineer were satisfied with a margin of 3 to 4 dB, it appears is reduce the transmitting power 500 watts to 20 to 30 watts. Or he might be willing to provide transmitting with a say transmitting power is equal to 100 watts. Since he may not want to consider additional trade-off, the engineer would start a new tabulation with a transmitting power of 100 watts and again performance the successive of link budget computations and to provide similarity numerations of possible between the trade-offs. Here the table that can recognize the uplink limited and downlink limited regions is the first few rows where the uplink SNR is high. A 3 dB degradation in the uplink SNR results in only the few tenths of decibel degradation to the overall SNR. If the system downlink limited, that is, the system is constrained primarily by its downlink parameters and hardly affected by the uplink parameters. In the bottom of few rows are tabulated in the below, we see that 3 dB degradation to the uplink effects and the overall SNR by almost 3 dB. Here the system uplink limited is system constrained primarily by the uplink parameters. Finally, we conclude this session one of many analyses that support a developing communication system. The link budget stands on its availability to provide overall system insight. By examining the link budget, one can learn many things about overall system design and performance. For example, from the link margin, one learns whether the system will meet the requirements comfortably or marginally or not at all. It will be evident if there are any hardware constraints and whether such constraints can be compensated for in other parts of a link. The link budget is often used for the consolidation system trade-off and configuration changes and understanding subsystem lacunas and the interdependencies. Together with other modeling techniques, the link budget can help predict weight size and cost. We have consideration how to formulate the link budget and how to might use it for the system trade-off. The link budget is one of the system manager most useful document. It is represents a bottom line tally in a search of optimum error performance of the system. So that's why link budget analysis plays a important role to fix the system analysis efficient parameter or system efficient parameter. Now we are discussing about some of the bits related to the satellite communication and satellite repeaters. Here the bit number 1, the satellite used as relay to extend the communication distance is called as A. Satellite, B. Communication satellites, C. Repeated satellites, and D. Geosynchronous satellites. Yes, the answer is B. Why it is B? Communication satellites are not originators for information to be transmitted. If a transmitting station cannot communicate directly with one or more receiving stations because line of sight restrictions, a satellite can be used. This transmitting station sends the information to the satellites, which in turn retransmit it to the receiving station. So that's why the satellites that is used in the relay to extend the communication distance is called as a simply a communication satellites. Now coming to the next bit, the transmitter receiver combinations in a satellite is known as A. Relay, B. Repeater, C. Transponder, and D. Duplexer. In the previous slides of maximum part, we are discussed about transponder. So what do you mean by the transponder means? The transponder is the combination of a transmitter and a receiver combination. So that's why answer is C. The transmitter receiver combination in the satellites we known as a transponder. The basic function of a transponder are the amplification and the frequency translation. Once again I repeat, the basic function of a transponder is amplification and frequency translation. This reason the frequency translation in the transponder cannot transmit and receive the same frequency. Coming to the next bit, the downlink frequency. The downlink frequency is lower than the uplink frequency. We have to say whether it is true or false. Answer is yes, it is true. The original signal being transmitted from the earth station to the satellite is called as the uplink, and retransmitted the signal to the satellite to the receiving station is called as a downlink. Usually, downlink frequency is lower than the uplink frequency. A typical link frequency is 6 GHz and a common link frequency is at 4 GHz taken as an example. So that's why the downlink frequency is lower than uplink frequency always. And coming to the next bit, we have to discuss what is the reason for carrying multiple transponder in the satellites. We have to fix one or more transponder in the satellites. The reason of A, more number of operating channels, B, better reception, C, more gain, D, redundancy. Answer is A. Because of economically feasible, the satellite must be capable handling several channels. As a resultant, most satellites containing multiple transponders, each operating at each different. Each transponder represents an individual communication channel. Once again I repeat, maximum number of transponder we are using. supposed to get what's the number of channels. More satellites contain multiple transponders because of each transponder will allocate for one defined frequency. In order to transfer more number of operating channels, we need more transponders in the satellite. Coming to the next bit, why VHF and UHF microwave signals used in satellite communication? Option A for more bandwidth, option B for more spectrum space, option C are not diffracted from the ionosphere, option D economically valuable. Answer C is are not diffracted from. Option C is the right answer. Why it is option C? VHF and UHF and microwave signals penetrate the ionosphere with a little or no attenuation and are not refracted to the earth. Lower frequency undergoes the total internal refraction and get reflected back to the earth. So that's why we are supposed to use VHF and UHF microwave signals in satellite communication. And now coming to the next bit, what is the reason for shifting from C to Ku band in a satellite communication? Option A, less attenuation. Option B, less power requirements. Option C, more bandwidth. And option D, overcrowding. What is the answer? It is simply answer is overcrowding. Simply. Why it is D? Most of new communication satellites will operate in the Ku band. The upward shift in a frequency is happening because the C band is overcrowded. Many communication satellites are in the orbit now, most of the operating in C band. However, there is some difficulty with interfacing because of heavy usage. The only one way the interference will be minimized to shift all future satellites communication to higher frequencies. So that's why we are shifting the particular C band to Ku band in the satellite communication. Now coming to the next bit, which of the following bands are not used in the satellite communication? First one is the MF, second one is the Ku, third one is the X band, and next one is the C band. So answer is A. We are not supposed to use MF band. MF is the lower frequency band than Ku, C, and X bands, and it doesn't lie on the microwave spectrum. Microwaves are used for the satellite communication since lower bands get reflected from the ionosphere. Previously, we told that only VHF and UHF and microwave range frequency of bands only will supporting for the satellite communication. Apart from that, remaining all bands will not supportable for satellite communication. So that's why the range locating in the VHF and UHF and microwave are supposed to use for better propagations with less probability error in satellite communication. Now coming to the next bit, what is the maximum theoretical data rate of the data rate if the transponder is used for binary transmission with a bandwidth of 36 MHz? Answer 32 Mbps, 72 Mbps, 36 Mbps, 12 Mbps. Yes, the answer is B. For a binary transmission, the maximum theoretical data rate or channel capacity of C is given by C is equal to 2B. That implies C into 36 MHz, that is equal to 72 Mbps. So that's why the answer is 72 Mbps, option B. And coming to the next bit, why are techniques like a frequency reuse and spatial isolation carried out. Option A, reduce the traffic load. Option B, more gain. Option C, high speed. Option D, error detection. Answer, simply answer A. Why it is A? At times there is more traffic than there is transponder to be handled each. For this reason, numerous techniques have been developed to efficiently increasing the bandwidth and signal carrying capacity of the satellite. Two of these techniques are known as frequency reuse and spatial isolation. That means by using of a frequency reuse and spatial isolation, we are supposed to reduce the traffic load in satellite communication. Coming to the next bit, which techniques uses two different antennas to reduce the traffic on the same frequency. Once again I repeat, which techniques uses two different antennas to reduce the traffic on the same frequency? Option A, spatial isolation. Option B, frequency reuse. Option C, multiplexing. And option D, modulation. Answer is option B. In the frequency reuse technique, two systems use the same frequency, although operating on extremely the same frequencies. They are isolated from each other by using of special antenna techniques. For example, a virtual polarized antenna will not respond to the horizontal polarized signal and vice versa. On left hand, circularly polarized antennas will respond a right circularly polarized signal and vice versa. So that's why we go for the frequency reuse concept. And coming to the next bit, which technique uses spot beam antenna to divide the area of coverage by satellite into smaller segments? Option A, spatial isolation. Option B, frequency reuse. Option C, multiplexing, and last one is the modulation. Yes, the answer is spatial isolation. By using narrow beam or spot beam antennas, the area on the earth covered by the satellite can be divided into small segments. Each station in each segment may actually use the same frequency, but frequencies are very narrow beam width antennas. There is no interface in between the adjacent segments. Now coming to the last bit, spatial division multiplexing access depends on the satellite location and not a frequency. Once again I repeat, SDMA depends on satellite location and not on frequency. Whether we have to judge whether it is true or false. Yes, answer is true. Spatial dimension multiple access uses the spatial isolation technique. Earth stations in each segment may actually use the same frequency, but because of very narrow beam widths of antennas, there is no interference between the adjacent segments. The technique is referred to a spatial division multiple access. In the access to the satellite depends on the location but not on frequency. By now we discussed the topics sample link analysis. In the sample link analysis, we detailed about link budget with a suitable example. By considering the frequency of 8 GHz, range is 21,915 nautical miles. And after that we are deals with some of the points, discuss about the sample link, and after that we discuss about the receiver figure merit and the receiver isotropic power, and also we calculate receiver isotropic power based on the power, loss and temperature with respect to gain. And after that we discuss about a few topics based on satellite repeaters, non-regenerative repeaters used in the satellites, and also we declare the formula for PR, receiving power, and also ratio between receiving power with respect to noise, and also we analysis Satellite repeaters with a 10 users with uplink frequency of 375 MHz and downlink frequency of 275 MHz with a 22,000 nautical miles as an example. And after that, we discuss about non-linear repeat amplifiers. And finally, the particular topic will conclude with the system trade-off. In the system trade-off, we balancing the sheet of receiving power with respect to noise by considering of all margins values. And finally, we will conclude this topic with some multiple choice bits based on satellite repeaters. Thank you.